And with that, I'd like to introduce Ron Genova, the CEO of Third Order Technologies, Nanotechnologies. Thank you, David. Appreciate it.
A little bit of logistics here.
Yeah, I'm sorry. I want to apologize. We had a little glitch this morning with the PowerPoints, and they're all being loaded in as we go along, which
we're there.
Seems like we're okay right now. Thank you, Ron.
Great. Good morning, everyone. I appreciate the opportunity to present to you today. My name's Ron Genova. I'm the CEO of Third Order Nano. One of the things that I'd like to do with you, just to start off, of course, we need to make our lawyers happy and put our safe harbor statement in here. These will be some forward-looking statements, but assuming that the coffee is all kicked in, everyone's got their caffeine and is ready to rock and roll, let's talk a little bit about the vision of our company. You know, it's kind of interesting. If you think about what material, and I'm sure this is not something that you fall asleep at night thinking about, but if you think about what material in the last century, in the 20th century, really defined the century, if you think about it a little bit, you probably come up to the conclusion that it was silicon. I mean, if you think about the things that are clipped to your waist and the things that are in front of you on your desks every day and all the things in the houses and the offices that we work on, they're all based with silicon, the silicon microchip and the sort of things that gave birth to. But now here's the question. Will silicon be the material for the 21st century, or will another material take its place? And honestly, I believe that our revision for our plastic materials will really be the material that could very well define the 21st century. Now, that's a very big statement for a very small company, but I hope to convince you as we go forward with this presentation why I feel so strongly about that. And the real key to making this happen is solving this thing, this Achilles heel that has kept polymers from mass production for a very long time, and that's the fact that they're traditionally unstable. We'll tell you how we fixed that and how we took a different approach. So anyway, where would we use this plastic materials? Well, there's quite a number of applications. It's really the multi-billion-dollar information movement and management industries, and there's quite a lot of them. There's also a number of other places where these types of electro-optically active polymers and plastics can be used, but these alone are just absolutely huge markets. And the one that we're really picking, although there are some security and defense activities that are going on, the main area that we're continuing to focus on is the information movement and management, really the plumbing, if you will, of the internet. Bandwidth is increasing by 50 to 100% per year. The 10 gigabit per second, which is the high-speed backbone that's running our country, that's actually exhausted right now. There's a lot of choke points in that. Even though in the telecom boom, a tremendous amount of capacity has been built up, what's happened is that capacity has largely been exhausted. And new services that are coming down the pike very quickly, like the video casting, are going to consume huge amounts of bandwidth. So if you take a look at the internet traffic, and this is, I like our engineering guys say, it's a log-log scale. But what that means is the fact that if you take a look between the years, about every 2 to 3 years, the demand for traffic absolutely doubles, to the point where we're doing 1 terabit per second. Now, you know, many of you think about, gee, I had a 56K modem not too very long ago, and we thought that was great. Well, think about this, because that's 1 billion kilobits per second that's going over the backbone traffic. Now, over here on the right-hand side, you can see how did the networks handle this? Well, we started off life at 50 megabits per second, and I was in Bell Labs when we were doing that, and we thought, boy, this is duck soup. We did the Northeast Corridor. We would never have to go any faster than that. I mean, who could consume 50 megabits per second? Well, the reality is that we continued to creep up and up and up until we got to 2.5 gigabits. And then everyone said, that's it. That's as fast as we're ever going to go. Let's concentrate on putting more information on different colors of light, and that's how we'll go forward, called DWDM, if any of you are familiar with the industry. Well, the reality is that didn't happen. 10 gigabits came along, and now that's exhausted. Where do we go from here? The rule of thumb is that you go up by a factor of 4, and cost can go up by no more than a factor of 2. Able to get that 4x jump in speed and the 2x increase in cost is what's really caused this big delay. But I think that history is about ready to repeat itself. Let's go back in time just a little bit. 1996 to 2000, the network was at 2.5. One company, Nortel, said, you know, I believe in DWDM and I think it's important, but I think it's just as applicable at 10 gigabits per second. And just how we one time thought that 50 megabits was as fast as you'll ever need to go, we believe that information is where it's at. So we're going to bet our company. Frank Dunn says, we're going to bet our company, Nortel, on 10 gigabits. Well, only one company actually had the technology that could go 10 gigabits per second, and it turned out it was AT&T in the Bell Labs group. So what happened? Well, we have a lithium niobate technology. That's this little puppy. This little guy costs more than $10,000 when it first came out. The only technology that could act as a shutter to turn light on and off 10 billion times per second. So with that, Nortel launches into the 10 gigabit world. In October of 95, their stock was $39. At the end of 99, their stock was $550. And as you can see on the chart, or maybe you can't because it's a little tough to see, but it did peak at over 800 before the telecom bubble burst. It turned out that AT&T actually won pretty big on this as well, because the modulator business grew to over $1.2 billion in just 3 years. Rich McGinn, Carly Fiorino, they went out on the roadshow, they launched Lucent Technologies and resulted in a huge market cap. I actually lived this thing. I was the guy that ran the modulator business when we got it going. So let's take a look at today, 2007 and beyond. The backbone's at 10, it's going to move to 40. All of the other switch companies learned the lesson from Nortel. So there's not going to be one that's going to lead the pack. Everyone wants to go to 40. Everyone recognizes we need it, and everyone also recognizes that the lithium niobate Rockstar doesn't do 40 gigabits. There needs to be another technology. And even if you could get lithium niobate to do it, you can't get the costs down to the point where they need to be. So we believe that Third Order Nanotechnologies has this new technology. Our 40 gigabit position to be, I think, the upcoming rock star for this particular industry, and you can do the math. At the end of the day, I believe that the TDON shareholders are going to be happy campers. You know, we've talked about electro-optic materials, and a lot of very large companies, IBM, DuPont, Host Celanese, lots of them, Intel, have all looked at these huge markets, and literally billions of dollars have been spent trying to get polymers mass commercialized. You know, smaller, faster, cheaper, less power, it's all the right kinds of things. Why hasn't it happened? And it's because of these problems with stability. So what did Third Order Nano do? Why are we the company that we think is going to go out and do some great things? Well, you know, you've heard this, I'm sure. The definition of insanity is when you try to do the same things in the same way and you expect different results. Well, believe it or not, but that's actually more than, you know, billions of dollars have been spent by companies doing exactly that, because these electro-optically active molecules were thought to only work one way. And that way was governed by a theory called BLA, bond length alternation. And what that means is you take a donor here and you take an acceptor here, and then you link these little carbon atoms between them, and that's what makes the current and the photons pass through. But what happens is every time that you build these little bridges and you stretch the donor, you get better performance electro-optically, but you also get worse stability. Net-net, the more you do to make the molecule better, the worse it gets. So, like the Wright brothers found out, the only way to really predict the future is to create it. And we believe that's what we've done. We've created the future because what we did was we took the problem and we turned it on its side. We said, you know, if hundreds of millions of dollars have been spent just in trying to get these polymers to be stable, you know, how could we go ahead and fix this problem? And we said, all right, let's look at it this way. We've got an unstable situation here. Let's take a very stable molecular structure, something like carbon, benzene rings, if you will, very, very stable molecular structures. And let's make it electro-optically active. And they said, well, it can't be done. And the reality is that we've actually done it. It's taken 15 years, but we have done it, and we've demonstrated it. And we're very proud of the fact that Dr. Fred Goetz's theories have proven out exactly as predicted. Now, this is a kind of an interesting chart. I won't spend too much time on it. But if you take a look at this, Lumira has what used to be called the best-in-the-class electro-optic polymers. LMRA is their trade symbol. And you can see the donor and the acceptor, and as my daughter says, gee, Dad, that's kind of like the Indiana Jones movie. You know, it's kind of walking across this big gorge with this kind of suspension bridge. You imagine yourself up there and how unstable that is. Well, what we did was by making our molecule out of completely cyclical rings, our bridge across that gorge actually looks like a very solid bridge. And in fact, not only is it a solid bridge, but it's also much wider. So we can support traffic at 40 gigabits. We can support traffic at 100 gigabits. In fact, we can support traffic up to 500 gigabits per second. Now, how do we leverage this stability thing into future applications? So I'm borrowing from Ray Bradbury and the Star Trek people here, but we're going to boldly go where no photon has gone before. And how are we going to do that? Well, we're going to do that by getting into the all-optical information movement and management. See, our material has a very interesting effect. It's called the third-order effect. That's why we renamed our company Third Order. It uses light to control light. So one flavor of light, one color, if you will, can control another color, and that's the basis of the all-optical transistor. Many of you know from microprocessor world, the transistor was how the integrated circuit and the all-optical microprocessors got started. Now, there's a gentleman named Terry Turpin who has a company called Essex, and they're making analog optical computers. In fact, they're making them today. They've made 3. They are all living in agencies in the government that have just 3 letters. And they're using these to kind of sniff through the email traffic and all the cell phone conversations, and they're looking for keywords for homeland defense. But you know what? 50,000 times faster than a traditional computer isn't fast enough. Terry got very excited. We were talking with him at one of the Gilder conferences about 2 years ago, and we told him about our technology, and he's become very much a fan of it. He believes it can make it go at least 100 times faster. And so we're working on a development project to show that we could go 5 million times faster than a traditional computer, and that process is underway. So, hot off the press, well, not quite so hot anymore, but it was about a month ago now, we did a press announcement which internally we called our Intel on Plastic. And we talked about how we're going to be using our technology to become the next generation technology. Carine is the material. Now, this is not carine, but this is an idea. This looks like the old kind of things we used to make viewgrass on. Remember viewgrass before PowerPoint? Just a little piece of acetate film. This has hundreds of waveguide technologies on it. Now, people talk about, of course, silicon is the best thing. It's made from sand. How can you get cheaper than sand? Well, to refine the sand is very expensive. This is plastic. You make this in rolls like you make saran wrap. That's going to be inexpensive. That's the kind of thing that you need to make inexpensive microprocessors out of plastic. So we're very excited about having the technology to do that. We're also very excited about having a great team that's going to help us there. This is Dr. Fred Getz, the gentleman whose theories actually turned out to work as he had predicted many years ago. Terry Turpin from Essex Corporation, I'm happy to say, has recently agreed to serve on our board of advisors. Dr. Tang was a very interesting case study. Dr. Tang's been in the industry for many years. He worked with these early types of polymers, and he developed a polymer. He developed the first 40 gigabit modulator more than 10 years ago, except it was made out of these unstable products. It only lasted about 5 minutes in field applications, but he was proved that it could be done. He also invented the industry standard Tang-Man test, which defines how good a polymer is. Bottom line, Dr. Tang found out about our data, sat down with Fred Getz Jr., our chief technical officer, listened to her story, liked it so much, he joined our company. So that was a good news story, and we're also working with Photon X, which is an industry supplier that makes absolutely the best waveguides. So, just sort of to wrap up a little bit here, we changed our name back in October from SciTech, which no one would really know how to spell just by hearing it, and we made it to be Third Order, which is actually more reflective of what we do, and it's easier for brand identification. We've got revolutionary advancements. They've been 15 years in the making. It's a radical departure. We took that model and we turned it on its side. We did things entirely different, and that's what yielded this breakthrough. We've not only successfully demonstrated that we're better than the best competitive products, but that's been independently verified. So you don't have to take our word for it. Dr. Norwood at the University of Arizona did a number of tests and confirmed that. We've got a very strong IP position. We've got patents issued, several others pending, which we expect to issue very soon. Plus, we've got what we call the Coca-Cola formula. This is the sort of things that happen in the laboratories. We don't tell anybody how it's done. It's not disclosed in the patents, and that's really the secret sauce. We've got a very good scientific and advisory board and executive team. We've got several multi-billion-dollar markets that we're going to be able to get out into. In fact, the 40 gig is what we're going to have prototypes to this year. We've got strategic alliances and partners already underway. We're going to be looking to do more of those. We're getting some industry recognition and exposure now on a variety of places, including this conference. So, third order nanotechnologies, we like to call it, it's a quantum leap in thinking. What these represent are a new generation of electro-optic materials addressing worlds of opportunities. This is the point where David told me that the ceiling was going to open and the confetti and balloons would drop and the music would play and people would wipe tears from their eyes and get their checkbooks out. But yeah, that's later. Okay, great. Go ahead.
A couple of questions. You talked about, you addressed the patents, so there shouldn't be too much there. Isn't there a lot of energy that's going to be used in order to push this faster? That's one question. And will a regular computer work, or are you going to need a different computer? And this serene that you're talking about, it's a piece of plastic that is combustible, or, I mean, there are all kinds of things that could happen with the serene, and then I'm finished. Oh, one other question. Do you own most of the stock? Because if this is so great, they're going to buy the company off of you.
Okay, they're all very good questions, and let's see how good my short-term memory is. So first of all, yes, it will represent an entirely new and different type of structure, so it will be a new computer, it will be a new processor. That shouldn't be too much of an issue because, you know, everyone's sort of used to having a 3 or 4 year life expectancy on processors. And probably what will happen is initially we will use this technology integrated with existing technologies. I don't believe the all-optical computer will be on our desktops for quite some time. Is it combustible? Depending on how you make it, how you link this with a certain substrate, you can link it with non-flammables. Typically, that's not as much of an issue, though, because this would get put into the same sort of a little ceramic type of a package that you would have with a traditional integrated circuit. So you wouldn't have the combustible issues there. Most of the stock, I mean, there's more than 50% of the company is still closely held by its founders. And it is, in fact, a very inexpensive substrate to make. This has a very exotic crystal in it. This is plastic. It's almost an intuitive decision there. The energy, yeah, you know, that's what's kind of neat. You know, the energy, and thanks for bringing that up. The energy to run this takes about 12 volts of electrical signal power. And in terms of radio frequencies, 12 volts of signal power at a very high frequency, the higher you go, the more power it takes, the more heat, and all sorts of bad things happen. Plastic, turns out, it needs less than a tenth of the voltage that it would require to run this. I mean, this takes 12 volts. With 1.2 volts, you can move mountains. So the reality is it is smaller, faster, cheaper.
So it's more for
Yes. Now, really, the beauty of this, and that is a great question, the beauty of this is it's an entirely new material platform. And because of that, it's somewhat of a greenfield in terms of intellectual property. And being able to do modulators in this sense, well, I don't think there'll be any need for cross-licensing or for acquiring anyone else's patents.
I have two questions here. Right here.
There's here.
Number one, you talk about a patent estate. How many patents do you have? Is it just the U.S. or North America and the rest of the world? And then I have another question also, and that'll be it.
Sure. Well, I'll address the first one. Our patents are not every country in the world, but they are certainly a widespread number. It's the European Union. It's all of North America. Several areas in the Pacific Rim region, including China and Japan.
Have that been issued or pending?
There is one that is actually issued. There are 4 others that we've got an office notification that should issue hopefully within the next, say, sort of 6 to 10 weeks.
That's the U.S. Patent Office?
Correct.
Yeah, okay. The other question I have is you talk about stability, and I'm just wondering if you can, you talk about carbon atoms. How small are they?
Wow. You're talking actually down into the nanoscale?
That you're talking about in your product.
That's absolutely right. It's down into the nanoscale. So if you tried to correlate that, a blood cell is 6 microns. Then a micron is about 10,000 nanometers. So you're talking literally building things from the molecular level, atomic level up.
Okay. Thank you.
Thank you. Thank you very much.